Okay, now I'm going over number 7, where you're given a position graph and a velocity graph. The period of this thing is 1 second, clearly visualized by the velocity graph. And that means that when you draw the potential energy, you have to have it, you could have a negative value, say, let's say -2 to +2, and draw a bigger wave, but you have to have it 0 potential energy when the velocity is max. And so this is the way they've drawn it there. Note that the period would be there. So if you have a reasonable sine squared graph, and you have a maximum that's labeled times, so you've got to have a maxima at the beginning, at the middle when it's at its there, and another maxima back at 1 second when it returns to that position. So there's your thing. Having the maximum minimum of potential energy difference of about 0.16. Total mechanical energy is potential plus kinetic. You can find kinetic, and you know it's about 1.6 meters per second. It's its maximum kinetic energy. It has to have 0 potential. And so when you calculate E, it really comes out to be 1/2 mv squared, 0.16 joules. Okay? So at the position of maximal displacement, 0.16 joules, position of maximal kinetic energy, 0.16 joules. There. And for the last one, acceleration has to be maximal. It could be -10 or +10. You can have a sine or cosine. You get a point. Have to have the right phase relationship. When acceleration is maximal, the position is also maximal, so it's at the maximum lowest position or the maximum highest. And when the acceleration is lowest, here, this is when your maximal velocity must occur. You could solve all this, and you could get that acceleration is force divided by mass. Force is kx, Hooke's constant, the restoring force, and it's shown there, about 10 meters a second. You want to get 2 out of 3 points here.